Welcome to the RBFS Fundamentals Training Series. In contrast to many other networking concepts, quality of service is an end-to-end approach that must be supported across a variety of network devices, each with different capabilities. Configuring QoS in a network typically involves tuning parameters to match the specific hardware platforms in use. An additional layer of complexity is added when applying QoS to broadband network gateways that connect multiple subscribers across a physical interface. In this case, hierarchical QoS is required at different levels to manage traffic effectively. In this video, we'll cover some of the key fundamentals of QoS and discuss the basic building blocks used in RBFS. Please note, this training video is intended to introduce the concepts and is not a substitute for professional services when implementing more complex QoS designs. All configuration examples and demos are based on RBFS version 25.3.1. Before we begin, a quick heads up, this video is free to use for non-commercial purposes and is intended to support self-study with RBFS. Please note that it doesn't cover every possible configuration option, and implementations may evolve in future versions. Here's what we'll cover in this video. First, we'll provide a brief overview of QoS concepts and building blocks. Then, we'll dive into traffic classification, explaining how traffic is identified, grouped, and marked, with a look at the relevant header fields. In the policer section, we'll explain how an ingress policer is used to rate limit traffic. Next, we'll cover queues, which act as buffers to temporarily store packets before they are transmitted on an egress interface. Queues are critical for shaping traffic and preventing congestion. Finally, we'll discuss schedulers, which determine how packets in queues are prioritized and transmitted. In this section, we'll introduce the main ideas behind quality of service and take a high-level look at its components. Quality of service, or QoS, is a critical concept in IP networks. It ensures that traffic is managed efficiently by prioritizing different types of data. This becomes especially important in converged networks, where applications such as data, voice, and video all share the same infrastructure. In the past, each of these applications ran on its own dedicated network. Consolidating them into a single network has reduced costs, but it also means that very different requirements now have to be met simultaneously. You'll often hear the terms quality of service and class of service used interchangeably. Strictly speaking, QoS refers to mechanisms that operate at layer 3 and above, while QoS applies mainly at layer 2 of the OSI model. When we talk about QoS, there are several parameters that define how well it works. Bandwidth is the most obvious one, the overall capacity of a link or interface, usually measured in bits per second. In practice, packet lengths vary, and while capacity is often specified at layer 1, overhead from layer 2 and layer 3 headers reduces the effective throughput. Latency is another key factor. It describes the time a packet takes to travel from source to destination, and it's especially critical for voice communication. If latency becomes too high, the quality of experience drops noticeably. Sometimes latency is confused with delay, but latency refers specifically to end-to-end transmission time, while delay can include a variety of time lags introduced along the path. Closely related to latency is jitter, which reflects the variation in latency. When jitter is high, packets may arrive out of sequence, causing problems such as jerky video playback. Applications often use buffers to smooth out jitter, but this comes at the cost of additional delay. Finally, we have packet loss, the percentage of packets that are dropped during transmission. Traffic loss can occur because of congestion or be enforced deliberately when traffic violates service contracts. Protocols like TCP can retransmit lost packets, while UDP cannot, which makes careful QoS design essential to ensure each traffic stream is treated appropriately. Now let's break down the main functional building blocks of QoS. The process begins with classification, where packets are sorted into different types for further treatment. You can think of this step like sorting mail at a post office. The system looks at the labels or specific header fields to decide how each packet should be handled. RBFS supports two classifiers, the behavior aggregate classifier, which relies on existing QoS markings, and the multi-field classifier, which can match on any header field using access control lists. Once classified, packets may be subject to policing, which enforces ingress rate limits and ensures traffic stays within service contracts. Policing can drop packets or downgrade their markings if they exceed the allowed rate, preventing a single flow from overwhelming the network. Packets are then placed into queues, which act as packet buffers. Different priorities are stored in separate queues. At this stage, shaping can be applied, which smooths traffic by holding packets briefly to keep them within a desired rate. Unlike policing, shaping doesn't drop packets, it simply delays them slightly to reduce bursts. Congestion management techniques, such as random early detection, can also be applied while packets sit in queues. Random early detection works by proactively dropping a small number of packets when queue levels start rising. This early signal encourages senders to slow down before true congestion occurs. Next, scheduling determines how packets from different queues are selected for transmission, effectively deciding how bandwidth is allocated among traffic classes. For example, strict priority scheduling always serves high-priority queues first, while weighted fair queuing gives each class a guaranteed share of bandwidth. Finally, remarking adjusts the QoS markings in packet headers before packets leave the switch. This ensures packets exit the device with markings that match the network's policies, for example, correcting traffic that entered with inappropriate or overly optimistic markings. Let's now look at how QoS is implemented in hardware. RBFS runs on whitebox switches built on Broadcom's Qumran ASIC family, including Q2A, Q2C, and QAX. An ASIC, or application-specific integrated circuit, is a chip designed to perform networking functions at very high speed using fixed hardware pipelines. The scalability of QoS features, such as the number and size of queues or policers, depends heavily on the resources available on each chip. Proper QoS design must therefore take ASIC limitations into account. In a Q2C ASIC, packets move through a fixed processing pipeline. First, the ingress packet processing block extracts metadata from packet headers and performs classification and lookups. Next, the ingress traffic manager provides buffering and policing. This block also implements virtual output queuing, meaning that although queuing is logically part of egress processing, the physical queues actually reside on the ingress side to avoid sending packets toward congested outputs. After the ingress traffic manager, packets reach a block that provides an interface to a fabric ASIC. This interface is used only in modular systems where multiple forwarding ASICs are connected, for example, a chassis with separate line cards. As of version 25.3.1, RBFS supports only standalone switches with a single Broadcom Qumran ASIC. Because of this, the fabric interface is bypassed, and packets are sent directly to the egress traffic manager, which handles shaping and scheduling. Finally, the egress packet processing block rewrites packet headers before transmission. The Q2C ASIC can also connect to an external knowledge base processor, which offloads certain functions such as statistics collection or multi-field classification. Not all traffic simply passes through the switch. Some traffic, such as routing protocol packets or management traffic, is redirected to the CPU for processing. This path, known as the host path, has limited bandwidth, so QoS policies may need to provide special treatment to ensure critical control plane traffic is not starved. A forwarding class is a mechanism used to group data packets based on their service requirements. It allows network devices to prioritize and manage traffic differently, depending on how important that traffic is. In RBFS, there are 8 forwarding classes, named Class 0 through Class 7. Each packet is assigned to one of these classes using either a behavior aggregate classifier or a multi-field classifier. If no classifier makes an explicit assignment, the packet automatically goes into Class 0. It's also possible for the forwarding class of a packet to change as it moves through the processing pipeline. The forwarding class determines how a packet is handled inside the network device. Each class is mapped to a specific output queue on a switch, and the queue it lands in dictates how the packet will be scheduled. Before we dive into individual QoS components, we'll introduce the QoS profile, which is a configuration template that defines how network traffic is prioritized and managed. A QoS profile contains one or more components, for example, a classifier, a policer, queue definitions, and a scheduler. QoS profiles are used to enforce quality of service on network interfaces or subscriber sessions, ensuring that critical traffic receives better treatment than less important traffic. RBFS supports assigning QoS profiles to subscriber sessions using the setAccessAccessProfile command, or to physical or logical interfaces using the setInterfaceInterfaceNameClassOfService command. In this section, we'll explore classification and marking. We've already seen where they fit into the pipeline during the packet walk example. Traffic classification is the process of identifying and categorizing network traffic into forwarding classes, based on predefined criteria. This step is foundational in QoS, as it groups traffic with similar requirements for further processing. For example, voice traffic, which requires low latency, is placed in a separate class. Video traffic, which is highly sensitive to jitter, is placed in another class, while web browsing is grouped differently again. In most cases, classification relies on fields in packet headers. Examples include VLAN IDs in Layer 2 frames, source or destination IP addresses and protocol numbers in Layer 3 packets, and port numbers in Layer 4 datagrams or segments. A major challenge in QoS is maintaining consistency across the network. All devices must apply the same classification rules to ensure packets are not reclassified along the path. Likewise, QoS treatments must remain consistent. If even a single device applies different handling to a packet, the entire end-to-end service can be compromised. Typically, when QoS is used, the network has a service contract with its users or customers. This contract defines the services offered and specifies performance parameters. Classification at the edge of the network, where traffic enters, is especially important, because the network should not trust QoS markings set by third parties. At this point, the network also decides whether traffic is in contract or out of contract. Before we move on to the details of classification, let's first discuss traffic marking. Traffic marking is the process of tagging packets with priority values to inform subsequent devices how those packets should be treated. As mentioned earlier, deep classification is usually performed at the ingress of the network. To avoid implementing complex classification rules on every individual device, packets are marked with priority values that correspond to traffic classes. This makes classification easier and more consistent across the network. At each layer, specific header fields can be used for this purpose. Ethernet, the most common Layer 2 technology today, does not have a dedicated header field for frame priority. The Ethernet header only contains the destination MAC address, source MAC address, and type field. The IEEE 802.1p standard defines a priority code point, also known as the class of service field. This field is 3 bits long and allows values from 0 to 7, where 0 represents low priority frames and 7 represents high priority frames. The PCP value is carried inside the VLAN header defined in IEEE 802.1q. If VLANs are not used but priority tagging is required, frames can be sent with VLAN ID 0. Additionally, the VLAN header includes a 1-bit drop eligibility indicator, which can be used for active queue management. The advantage of Ethernet CoS is that classification can occur at the MAC layer before the IP header is inspected, enabling QoS handling on devices that do not support IP, such as Layer 2 switches. In backbone networks using MPLS, QoS marking is carried inside the shim header. The original specification defined a 3-bit experimental field without a dedicated purpose. RFC 5462 later renamed this field to the traffic class field, reflecting its primary use. Values again range from 0 for low priority to 7 for high priority. The IETF has defined several QoS models for MPLS networks, with the MPLS QoS architecture outlined in RFC 3270. We won't go into further detail here, but note that MPLS does not include a dedicated bit for congestion notification. Both IPv4 and IPv6 include an 8-bit QoS marker in their headers. The IPv4 header, first defined in RFC 791, named this field the type of service. The three most significant bits of the type of service field are called IP precedence, providing priority values from 0 to 7. The next 3 bits were originally used to signal delay, throughput, and reliability for active queue management, while the remaining 2 bits were unused. In contrast, the IPv6 header defined in RFC 2460 includes an 8-bit traffic class field without prescribing a specific interpretation. Since IPv4 and IPv6 are used side by side in modern networks, it makes little sense to maintain different QoS models for each. Several specifications therefore define unified frameworks that apply to both protocols. The most commonly used QoS framework today is the Differentiated Services Model, or DiffServ, which is a class-based QoS model defined in RFC 2475. A key concept of the DiffServ model is per-hop behavior, meaning that each device in the network applies its QoS treatment independently. This is similar to IP routing, where each router performs its own route lookup. The main advantage of per-hop behavior is that it reduces the need for soft states in the network and aggregates traffic streams, resulting in improved scalability. An alternative model, which is no longer used in modern networks, is integrated services. IntServ signals a dedicated end-to-end QoS resource, similar to circuit-switched networks. Its advantage is that services receive guaranteed resources, such as bandwidth. However, as the number of traffic streams increases, IntServ does not scale well. With the introduction of the DiffServ model, the type of service marker in IPv4 and IPv6 headers was redefined as a 6-bit field called the DiffServ code point. Several service definitions exist for the DSCP field. For example, the class selector uses only the 3 most significant bits, providing backward compatibility with IP precedence values. In addition, assured forwarding and expedited forwarding were defined. Assured forwarding includes 4 classes, AF1 to AF4, and 3 levels of drop priority for congestion management. For instance, AF41 represents class 4 with drop probability 1. Expedited forwarding was designed to transport low loss, low latency, and low jitter traffic, primarily voice. Since the DSCP field uses only 6 bits, the 2 least significant bits of the type of service field can be used for explicit congestion notification, as defined in RFC 3168. Let's return to the classification process. RBFS supports 2 types of classification, the behavior aggregate classifier and the multi-field classifier. In the DiffServ architecture we just discussed, traffic is classified and assigned to behavior aggregates. Each behavior aggregate is identified by a single DSCP value. The main idea is to perform this assignment only once at the ingress of the network. Within a DiffServ domain, devices trust the header markings and forward packets according to the per-hop behavior associated with the DSCP value. The behavior aggregate classifier is a simple mechanism based on the DSCP field. It is the first QoS function in the packet processing pipeline. For Layer 2 or MPLS traffic, the Ethernet PCP or MPLS traffic class fields are evaluated. Because the BA classifier cannot use other header fields, it remains very simple and highly scalable. It is best suited for core devices that do not interface with third parties. Now it's time to put this into practice and configure a behavior aggregate classifier on an RBFS system. Since QoS is only supported on hardware devices, we've set up a very simple lab that consists of a single Q2A based switch running RBFS version 25.3.1. The image used is of the multi-service edge type. The switch is connected to a Linux server running an application called BNG Blaster. BNG Blaster is an open-source network tester for routing and access protocols, actively maintained and developed by Rtbrick. For more information, you can visit the project documentation on GitHub. We'll use BNG Blaster to generate 4 different traffic streams with different type of service field settings and different destination IPv4 addresses to demonstrate QoS functions. All configuration related to QoS starts with the command set forwarding options class of service. Using the question mark for help, we can see that there are several subcommands for each individual building block. We'll walk through them step by step. In this first demo, we'll configure a BA classifier. Since a BA classifier relies on a single header field, it's straightforward to configure. You simply assign a classifier name using set forwarding options class of service classifier name. We name ours BA_example. Next, we define the classifier type. Here, we choose IPv4 type of service. Then we define a code point and map it to a class. Code point 0 is mapped to class 0. Similarly, we map code point 32 to class 1, code point 64 to class 2, and code point 160 to class 3. These code points represent class selector 1, class selector 2, and class selector 5. Earlier, we mentioned that QoS components are applied using a QoS profile, so let's define a simple profile using set forwarding options class of service profile. We name the profile QoS_profile and assign the BA classifier to it using the classifier name statement. Finally, we need to apply this QoS profile to an interface. Our BNG Blaster is connected to interfaces IFP 0/0/12 and IFP 0/0/20, so we bind the profile to these interfaces using set interface IFP 0/0/12 unit 0 class of service. We repeat the step for IFP 0/0/20. After committing the configuration, the show QoS classifier command confirms that we now have a BA classifier that maps 4 code points to 4 forwarding classes. The show QoS interface command shows that the QoS profile is bound to the corresponding interfaces. The show interface IFL 0/0/12/0 statistics command provides packet statistics. However, this output only shows egress classes, so we need to check IFL 0/0/20/0 instead. Doing so, we can see that packets are being assigned to class 0 through class 3. This slide summarizes the configuration we just performed for your reference. Defining a behavior aggregate classifier simply includes specifying the classifier name, the type of QoS marker, and the mapping of a code point to a forwarding class. Once defined, the BA classifier can be applied to a QoS service profile, which can then be associated with either access subscriber profiles or interfaces. For MPLS, the BA classifier can be assigned globally or on a per-instance basis, which is especially useful in MPLS VPN services. At the edge of the network, where QoS markings in packet headers cannot be trusted, multi-field classifiers are used. Multi-field classifiers are based on the concept of access lists and provide greater granularity by allowing matches on virtually all IP header fields. A multi-field classifier can also match on the type of service or traffic class field in the IP header, similar to a BA classifier. However, it is important to note that it matches the actual header value, rather than the value resulting from remarking at the BA classifier level. The remarking value is stored in internal metadata and is enforced only at the end of the pipeline. Multi-field classifiers can consume significant ASIC resources. If supported, multi-field classification can be offloaded from the ASIC to a knowledge base processor. Let's switch back to the CLI of our device and configure the multi-field classifier. The multi-field classifier is configured using the set forwarding options class of service multi-field classifier ACL command. You need to specify whether the rule is for IPv4 or IPv6. In our example, we set it to L3v4. Next, we define a classifier name using the rule name statement. Similar to access control lists, a multi-field classifier can have multiple entries, called ordinals, each identified by an ordinal number. At this stage, you configure a match block to define which packets should be classified, an action block to describe how to classify the packets, and a priority to set the level of importance. The BNG Blaster currently sends 4 traffic streams, as we saw in the previous example, 1 stream for each forwarding class. We now move the stream from class 1 to class 0 by matching its destination IPv4 address. After defining the multi-field classifier itself, we need to associate it with the QoS profile using the set forwarding options class of service profile name multi-field classifier name command. Once the configuration is activated, we can verify it using the show QoS multi-field classifier command. We can also verify the classification on the egress interface. First, we clear the interface statistics to see the effect more clearly. Upon inspecting the egress interface, we observe that there are no packets in class 1 anymore, but the number of packets in class 0 is twice that of class 2 and class 3. This confirms that we have successfully reclassified one traffic stream. As we just demonstrated, a multi-field classifier typically contains multiple rules, called ordinals, similar to standard access control lists. It also has a type, either IPv4 or IPv6, because the header fields differ slightly between the two protocols. Each ordinal includes one or more match criteria and a set of actions. The supported match types depend on whether the rule is for IPv4 or IPv6, and they include common header fields such as source and destination IP addresses, protocol numbers, and source and destination ports. A standard action is assigning the packet to a forwarding class. Like BA classifiers, multi-field classifiers are usually assigned to a QoS profile. Alternatively, they can be bound globally to cover all interfaces. Remarking is the process of changing the QoS marker in a packet's header. It usually happens at the edge of the network, where traffic from untrusted sources is adjusted to match the network's QoS policies and service definitions. The remarking block is the final stage in the packet processing pipeline. We explain it here because it is closely related to BA classifiers. RBFS supports remarking for Ethernet frames, MPLS frames, and IP packets. However, IPv4 and IPv6 remarking cannot be configured separately. In practice, remarking changes one code point value to another. It can also consider traffic color, set by an ingress policer, to assign different code points for out-of-contract traffic. By default, RBFS runs in MPLS uniform mode. This means it automatically copies the three most significant bits from the IP type of service or traffic class field into the MPLS EXP field. Just like BA classifiers, MPLS remark maps can be applied globally or on a per-instance basis. We've configured two classifiers so far. Before we move on to setting up remarking, let's quickly check which types of packets we're receiving from the BNG blaster, and which ones we're forwarding. To do this, we create a port mirror called test. Since we don't have an interface with an analyzer attached, we mirror the traffic to the CPU of the switch. Next, we specify that we want to inspect ingress traffic on interface IFP 0/0/12. We can view the results by starting the mirror with the capture mirror command. The output appears in hex format, but it's easy to verify that the IPv4 packets received have type of service values of 0, 32, 64, and 160. These correspond to best effort traffic, as well as class selector 1, 2, and 5. We then redefine the port mirror configuration to analyze the egress direction of interface IFP 0/0/20. Again, we can confirm that packets with the previously mentioned type of service fields are being forwarded. Now, let's define a remark map using the command, set forwarding options class of service remark map name IPv4, TOS. Here, we need to map a combination of the original code point and color to a new code point. In this example, we remark code point 64, which represents class selector 2, to code point 96, representing class selector 3. Since we don't have any policer configured, we simply set the color to all. Next, we must associate this QoS function with a QoS profile using the command, set forwarding options class of service profile name remark map name. After committing the configuration, we inspect the output of interface IFP 0/0/20 again. From the results, we can confirm that packets previously tagged with 0x40 are now tagged with 0x60. However, there's a downside: all other packets have been remarked to code point 0. This is the default behavior. Any code point that isn't explicitly configured is automatically set to 0. To fix this, we'll add 2 additional mappings. To summarize, a remark map consists of a name and a remark type. It maps the original code point to a new remark code point. The traffic color can be set to green, yellow, or all, with the color determined by the ingress policer. If no ingress policer is present, all packets are assumed to be green. The remark map is typically applied to a QoS profile. Alternatively, it can also be bound globally or on a per-instance basis. In addition to egress remarking, RBFS also supports ingress remarking, which can simplify device configuration. Both the behavior aggregate and multi-field classifiers offer a remark code point option to define remarking in a single step. It is important to note that the packet header itself is updated in the egress packet processing block before transmission. The remark code point set by the behavior aggregate or multi-field classifier is stored in the packet metadata inside the ASIC. The next building block in the QoS processing pipeline after classification is policing, which generally occurs on the ingress path. Policing is critical in modern networks to enforce traffic contracts and prevent congestion by ensuring that traffic entering the network does not exceed agreed-upon limits. Policing is the process that controls the amount of traffic entering the network. It works by monitoring the flow rates of traffic against a predefined threshold called the committed information rate. This is a key metric for ensuring that traffic does not exceed the agreed-upon limits, especially for real-time applications like voice or video, where consistent traffic rates are critical to avoid interruptions. If a traffic flow exceeds the CIR, the policer has 2 primary strategies to handle the excess traffic. Hard policing drops all packets that exceed the threshold, ensuring that no additional traffic flows past the CIR. Soft policing, on the other hand, modifies the priority of the packets, typically marking them with a color, often yellow, to indicate that the traffic is beyond the agreed CIR but is still allowed to pass under certain conditions. Even with soft policing, there's usually a limit on how much excess traffic is permitted. This limit is called the peak information rate. Any traffic exceeding the PIR is immediately dropped. This ensures that the network doesn't become overloaded and that critical services, like voice, are not affected by excessive traffic. Policers are essential for enforcing service-level agreements, ensuring that customers receive the bandwidth they're promised, and preventing oversubscription of network links. For example, if a customer's service is supposed to support 2G.711 voice channels, which equals 160 kilobits per second, the policer ensures that no more than 160 kilobits per second of traffic is allowed. If the customer tries to send more traffic, the policer drops the excess, ensuring that no more than the agreed bandwidth is used. In RBFS, policers are implemented as 2-rate, 3-color meters, as defined in RFC 2698. These meters operate in a 4-level cascaded mode, which allows for more granular control of traffic at different levels of priority. We'll go into more detail about cascaded policing shortly. Each policer level uses 2 token buckets. The first bucket is filled continuously at the committed information rate, and its size is referred to as the CIR burst size, or CBS. When a packet of size B arrives, the policer checks if there are enough tokens in the first bucket to allow the packet through. If there are enough tokens, the packet is marked green, forwarded, and B tokens are removed from the bucket. If there aren't enough tokens, the packet is marked yellow and passed to the second bucket. The second bucket, which is filled at the peak information rate minus the CIR, can hold a maximum of PBS minus CBS tokens. If enough tokens are available in this bucket, the packet remains yellow and is forwarded. If there aren't enough tokens in the second bucket, the packet is marked red and dropped. We have already mentioned that RBFS supports up to 4 levels of policing, with level 1 being the highest priority and level 4 the lowest, providing more control over how traffic is managed across different levels of priority. This hierarchical structure allows for efficient bandwidth utilization by enabling traffic at lower priority levels to use any unused tokens from higher priority levels. For example, if level 1 is configured with a CIR of 2 megabits per second but only 1 megabit per second of traffic is used, the remaining 1 megabit per second can be passed down to level 2. By default, RBFS allows this sharing of tokens across levels. To ensure strict traffic limits, max CIR or max peer can be configured. If the CIR and max CIR are set to the same value, no leftover tokens from higher levels will be used. Additionally, level 1 cannot inherit tokens from any higher level, as there is no level 0. Therefore, max CIR and max peer don't apply to level 1. RBFS supports up to 8 traffic classes, but only 4 policer levels, which means that multiple classes must be mapped to the same policer level. This mapping is defined using a class policer map. With class policer mapping, you can assign any class to any supported policer level. You can even map multiple classes to the same level if necessary. If a class is not explicitly assigned to a policer level, it bypasses policing entirely, meaning it is not subject to any rate limiting or priority-based modifications. Let's start by configuring a class policer map using the command set forwarding options class of service class policer map name. In our example, we'll name the map CPM_example. The map itself is configured with the command class name policer level. Earlier, we mapped DSCP0 to class 0, which represents best effort traffic and is thus our lowest priority. Since policer level 1 is the highest priority, we'll map class 0 to level 4, class 1 to level 3, class 2 to level 2, and class 3, which contains expedited forwarding traffic, to the highest policer level, level 1. Next, we bind the class policer map to our existing QoS profile using the class policer map name statement. Now, let's configure a policer named policer_example with the set forwarding options class of service policer command. While there are many options available, our focus is on configuring the rates for each of the 4 levels. At each level, you can configure several parameters. To keep things simple, we'll set the committed information rate to 5 megabits per second and the committed burst size to 4,200 kilobits. For level 4, we'll also set the max CIR to 7.5 megabits per second. Once configured, we bind the policer to our QoS profile using the policer name statement, so it gets applied to the interfaces. Oops, my mistake. After committing the configuration, we'll clear the interface statistics to observe the effect of the policer. The show interface IFL 0/0/12/0 statistics command reveals that packet drops are occurring at the ingress interface due to the policer. All 4 traffic streams are being sent at a rate of 10 megabits per second, but the policer levels are set to a CIR of 5 megabits per second, meaning approximately half of the packets at policer levels 1 and 2 are being dropped. Due to the multi-field classifier configuration, we don't have any packets in class 1, corresponding to policer level 3. Thus the unused CIR from policer level 3 is passed to level 4. And at level 4, we've not only set a CIR of 5 megabits per second, but also configured a max CIR of 7.5 megabits per second. As a result, we see that the number of accepted packets in level 4 is 1.5 times higher than in levels 1 and 2. Let's create a quick summary of CLI commands. When configuring policing in RBFS, there are 3 main steps. First, configure the class policer map, which assigns forwarding classes to policer levels. Remember that multiple classes can be mapped to the same level. Second, define the policer using the Set Forwarding Options class of service policer command. This allows you to specify parameters such as CIR and PAR for each level. Finally, apply both the class policer map and the policer to your QoS profile. Now that we've covered the classifiers and policers, let's move to the egress part of the packet processing pipeline and take a closer look at queuing and shaping. A queue is a buffer used to store packets before transmitting them. The need for queuing arises when an interface cannot transmit all incoming packets because they arrive faster than they can be sent. This is often the case on aggregation devices, where multiple customer-facing interfaces feed into a smaller number of upstream interfaces. In networking, queues are typically implemented as first-in first-out buffers, as they are simple to implement and can operate at wire speed. Packets are removed or dequeued from the head of the queue and stored or enqueued at the tail. There is no packet reordering in a FIFO queue. A critical parameter of a queue is its size, which determines how many packets it can store. If the queue is full, additional packets cannot be stored and tail drop occurs. Queue size depends on several factors, including ASIC memory and the type of traffic. A large queue can store more packets, reducing the likelihood of drops. However, larger queues can also introduce significant delay in end-to-end transmission, which is undesirable for latency-sensitive services such as voice. When a queue is full, newly arriving packets are discarded. This is known as tail drop. For some traffic types, discarding packets is preferable to introducing additional delay. However, other traffic types behave differently. TCP, for example, relies on acknowledgements to indicate which segments have been received. When packet loss occurs, TCP retransmits the missing segments, which results in additional traffic. TCP also uses congestion control mechanisms that reduce the transmission rate when congestion is detected and increase it when the network is uncongested. This process is known as slow start. If the network becomes congested and tail drops occur, packet loss can affect many TCP sessions simultaneously. As a result, all of these sessions may enter slow start at the same time, reducing their transmission rates and causing a significant drop in overall network utilization. This phenomenon is known as global synchronization. In the diagram on the right, multiple flows increase their transmission rate step by step until congestion occurs, after which they all enter slow start simultaneously. To improve network utilization, active queue management methods such as weighted random early detection can be used. The basic idea behind random early detection is to proactively drop a small number of packets at random before the queue becomes full. This way, only a subset of TCP sessions enters slow start rather than all of them. When configuring WRED, you define the queue fill thresholds at which random dropping begins. The drop probability increases linearly from the minimum threshold to the maximum threshold. Once the maximum threshold is reached, all packets are dropped. Note that WRED is useful only for TCP traffic, since TCP reacts to packet loss through congestion control mechanisms. For UDP, which lacks retransmission and congestion control, WRED is not appropriate. The traffic class to queue mapping defines how traffic classes are assigned to queues. Each class must map to a unique queue and two classes cannot share the same queue. Therefore, the class-to-queue relationship is strictly one-to-one. If a queue group is created with 4 queues, only class 0 through class 3 can be mapped within the class queue map. In RBFS, queues are defined using the Set Forwarding Options class of service quename command. The available configuration options include enabling header compression, adding a shaper to the queue, or configuring weighted random early detection. To keep this demo simple, we define only the queue size. We'll create 4 queues, best effort, low delay, low loss, and voice, and assign queue sizes to them. Queue size is specified in bytes. Next, we assign forwarding classes to queues by defining a class queue map using the set forwarding options class of service class QMap command. Our map is named CQM_example, and we assign class 0 to best effort, class 1 to low delay, class 2 to low loss, and class 3 to the voice queue. We then apply this configuration to our QoS profile using the class QMap name option of the set forwarding options class of service profile command. This slide summarizes the 3 configuration steps: defining the queues and their sizes, mapping forwarding classes to queues, and applying the class QMap to the QoS profile. Although we skipped the weighted random early detection configuration in the demo, we have included the necessary commands here for your reference. Our next building block is traffic shapers. Unlike policers, which drop out of contract packets at the ingress, shapers aim to smooth traffic flows to reduce packet loss during periods of congestion. When traffic exceeds a defined shaping rate, the excess is temporarily stored in a queue and then dequeued at a controlled fixed rate. This process helps prevent sudden bursts of traffic from overwhelming the network and causing packet drops. It is important to note that while shaping improves network stability and reduces loss, queuing packets introduces additional delay and jitter, which can negatively affect delay-sensitive applications such as voice or video. Therefore, shaping must be configured carefully based on the type of traffic being handled. In RBFS, shapers can be attached directly to queues to control traffic at a granular level or assigned to schedulers to shape traffic across multiple queues collectively. We will demonstrate the latter approach in the next section. Configuring traffic shapers in RBFS is done using the set forwarding options class of service shaper name command. This command provides several options, including shaping rate high and shaping rate low. Low-rate shaping is supported only for high-priority flows. Enabling low-rate shaping consumes additional QoS resources, which may impact scalability. Note that shaping rates may not be precise for fragmented data traffic. In our example, we define a simple shaper named sample_shaper with a shaping rate high of 10 gigabits per second. This slide summarizes the commands used to define a shaper. Shapers can be directly assigned to queues using the set forwarding options class of service queue shaper name command, or applied within schedulers, which we'll cover next. In this final section of our presentation, we'll explore queue scheduling. A scheduler is a quality of service function that controls the order and timing of packet transmission. When packets are stored in queues waiting to be sent, the scheduler decides which queue to serve next and how many packets, or bytes, to dequeue. This makes the scheduler a central component of QoS. It can prioritize critical traffic by serving certain queues first, but it can also ensure fairness by distributing bandwidth evenly across different traffic streams. There are several scheduling approaches. In priority scheduling, high-priority queues are served immediately as packets arrive, while low-priority queues are only served if no high-priority packets are present. This method is well suited for delay-sensitive applications such as voice, but it can lead to starvation of lower-priority queues, meaning their packets may never be transmitted. By contrast, fair queuing treats all queues equally, giving each a fair share of bandwidth and preventing starvation. An enhancement of this method is weighted fair queuing, where each queue is assigned a weight that determines its share of bandwidth. Higher weights result in more bandwidth being allocated to that queue. In practice, most QoS designs combine these strategies. For example, strict priority queuing may be used for voice and video traffic to guarantee low delay, while weighted fair queuing is applied to data traffic to balance efficiency and fairness. In RBFS, a scheduler is defined using the set forwarding options class of service scheduler name command. In our example, we name the scheduler sample_scheduler. After creating it, you need to define the type. As shown in the help output, RBFS supports a variety of scheduler types. For simplicity, we set our scheduler to strict priority. We also assign the shaper defined in the previous section to this scheduler using the shaper name statement. Next, we define a queue group using the set forwarding options class of service queuegroup command. A queue group represents a bundle of queues and can contain 1, 4, or 8 queues. We then create a scheduler map, which defines the relationship between queues and the scheduler, using the set forwarding options class of service scheduler map command. We name this map sample_map. Within the map, we associate the queue group we just created using the queuegroup name statement, and assign each queue to a priority level with the connection point statement. In strict priority scheduling, priority 0 is the highest. In our example, we assign priority 3 to the best effort queue, priority 2 to the low delay queue, priority 1 to the low loss queue, and priority 0 to the voice queue. We also assign our scheduler sample_scheduler as the parent scheduler name for each queue. Finally, we attach this scheduler map to our QoS profile using the set forwarding options class of service profile QoS_profile scheduler map name command and activate the configuration. Keep in mind that this is just a simple example to demonstrate the basic building blocks and how they relate to each other. A real QoS configuration is typically more complex and requires fine-tuning, for example, using different shapers for different queues. To verify and monitor the configuration, several commands are useful. The show QoS scheduler command lists all defined schedulers, including their type and assigned shaper. The show QoS scheduler map command displays the configured scheduler maps. The show QoS interface command lists all interfaces with their assigned QoS profiles. For more details on interface queues, you can use the show QoS queue interface name command. From this output, we can confirm that no weighted random early detection is configured. Finally, queue statistics can be retrieved with the show QoS queue counter interface name command. Let's wrap up the commands needed to configure scheduling in RBFS. The first step is to configure one or more schedulers using the set forwarding options class of service scheduler command. RBFS supports multiple scheduler types, including strict priority, weighted fair queuing, and combinations of basic scheduler types. Next, we configure a queue group, defining whether we want to use a single queue, 4 queues, or 8 queues. The scheduler map is created using the set forwarding options class of service scheduler map command. This involves mapping queues to specific parameters, such as the connection point. Finally, we assign the scheduler map to a QoS profile or interface. We'll conclude this video with a brief look at hierarchical QoS. So far, we've only looked at a single scheduler level. That works well for a single customer interface or a core network link. But things change when a BNG serves hundreds or even thousands of broadband subscribers over a single physical interface. Aggregation devices like OLTs or DPUs often don't handle QoS properly, because they aren't aware of traffic beyond layer 2. In these situations, it helps to apply QoS at multiple levels. You might enforce policies on the physical interface, on each VLAN, or even for individual users. RBFS supports hierarchical QoS, allowing up to 5 levels of scheduling. This means a scheduler can act as a parent to other schedulers, forming a hierarchy. In the figure on the right, we show a simple 2-level hierarchy. Scheduler 1 applies policies at the physical interface, while Scheduler 2 manages each VLAN as a child of Scheduler 1. This setup only makes sense if you have multiple VLANs on a single physical port. Hierarchical QoS helps ensure fair bandwidth distribution, prevent congestion, and give priority to critical traffic, even when thousands of subscribers share the same interface. I hope you enjoyed this video on configuring quality of service in RBFS. As mentioned at the beginning, this video aims to serve as an introduction helping you to understand the basic building blocks. Thanks for your attention, and see you soon in another video.